What we have been covering up to now, we're in the analysis part of the course, which is the second half of the course. We started by talking about asymptotic analysis and why do we analyze the code the way we are analyzing it. And then we dived into a number of techniques that we could use to analyze iterative code. We covered submissions, and last time we covered, for 2 lectures actually, amortized analysis, and today we'll look at randomized analysis. Afterwards, we will deal with recursive code. So let's start talking about randomized analysis. What is randomized analysis? It's the analysis of a piece of code that has one step that involves, or more, that involves randomization. So in the algorithm, there will be a randomly generated number, and based on the value of the randomly generated number, we make a decision or use that value to continue on with our algorithm. Not all algorithms will involve randomization. I'm referring simply to an algorithm that is rolling a dice or generating a number within a certain range, so let's say from 1 to 100, and based on the value that comes out, we do something. So our following steps after the random number generation is dependent on what value we get from the random process that we use to generate this random number. If you think of this carefully, the behavior of the algorithm will change every time you run it because it's based on what you get as an output. So if you're generating a random number between 1 and 100, if you get 2, it's different from getting 55, different from getting 71, different from getting 99, because the value, you are actually using it to do something. Okay? Whenever there is an algorithm that uses a randomly generated value as one of its steps, you'll have to analyze it using randomized analysis. Because we assume when we use submissions is that the code we're looking at, when we compute the number of steps, it's going to always be the same. When I write the submissions, for example, on any given piece of code that I try to analyze, and I define a lower term and an upper term to count the number of steps, say in a for loop, this is my understanding of what's going to happen. But if I'm having a random process, then you don't know the number of steps that will be executed because it's based on the output, or it's related to the output of the random process, or basically on the value, based on the value of the random number. And for that, we will use randomized analysis. Now, you might be wondering, did you see any or learn about any randomized algorithm or data structure before? And the answer is yes. Hash tables involve randomization. They use randomization. So to actually fully analyze the performance of hash tables, you have to do the exercise we already described in amortized analysis. And you have to do also a randomized analysis exercise on the performance of the hash table to really prove that it's order of O of 1. Because you have been learned since your early days of computer science education that hash tables are great, they are O of 1 data structure. But what you were not told is that actually O of 1 is not computed using submissions, it's computed using amortized analysis and also randomized analysis. And we will give it a special name. If it's randomized analysis, we're going to talk about it as expected O of 1. And since hash tables are actually employ randomization and employ amortization in the way they work, it is actually often described as you will see in the Corman textbook, expected amortized O of 1. Okay? So we will see this example. Now, you have already learned in this course an algorithm that uses randomization and rely heavily on randomization to work correctly, which is quicksort. Because if you remember, to pick the pivot, we rolled a dice and we picked the pivot being a random location. And I mentioned then, if you recall, or you can go and watch the video for the lecture of divide sort, of divide and conquer, that there is no better option than rolling a dice and figuring out or generating a random number between 0 and n-1, which is the number of possible entries in the array, and consequently picking that random value and using it as the pivot upon which we split left of the pivot and right of the pivot to be less than and greater than the pivot. So there are a number of actually algorithms that use randomization, and generally randomized algorithms are trying to solve a hard problem that you cannot solve deterministically, that you cannot solve by thinking through the problem and writing a piece of code that always executes the same number of steps for any given input. So it turns out that there is a very good chance, if you employ randomization in the right way, you will beat any deterministic performance. You will come up with a performance that is much better than without using randomization. Even though randomization sounds scary, because if you really think about it, you have no control on the output of the randomization process. So if you say I would like to generate a number between 1 and 100, maybe the range 1 to 10 is horrible for you. You never want to see any entry between 1 and 10 as an output of the random process, and you're happy with the rest from 20 to 100. But even with that even with that holding, even with that being the case, you still win overall with randomization if you employ it properly. And we will see examples of how much we can gain from a randomized algorithm. So what is randomized analysis then? Okay, what does randomized analysis involve? Well, it involves, and this is really the part that students get worried about when they see it, it involves the use of probability. Because a random process cannot be studied deterministically, because every time you get a different output. So we're going to use probabilities to figure out what is the asymptotic performance of a given piece of code that is involving randomization. Okay? Now, notice that there is a difference between randomization and amortization, because in amortization we plan the performance. In other words, we design in our algorithm a slow version and a fast version. Okay? So and the assumption is we are going to make some gain by slowing down, and we will benefit from this slowing down in the later process or the later operations or the later version that's going to be faster, as we've studied in amortized analysis. In randomization, we have no control. Okay, so it could go in any direction, the performance, but we will do the analysis using probability to figure out what's the probability of the bad case versus the probability of the good case, and if the probability of the good case is better, or is bigger basically, then we're happy. So even if we get the bad case because of an output of a randomization, on the long run, as we keep running the algorithm towards infinity, to infinity, actually we are actually winning. We are getting a better performance than any other way. Okay? And the general rule is, whenever you read about an algorithm and they tell you expected O of something, that means this is an algorithm that uses randomization, and this computed O of n, or O of log n, or O of n squared, or O of n log n. When they say before it is expected, that means the algorithm is utilizing randomization, and this asymptotic order was calculated using randomized analysis, which is the technique we're going to describe here. So it is not the regular kind of use of summations to reach to a conclusion about the big O, but actually it is a randomized analysis exercise. So let's go back and review some probability, okay? Because we're going to need this, and part of the material that I have given you since the first lecture about the master review that you need to go through involves probability. If you've already looked it up and start reading there, you would have noticed there are some probability rules. Okay? Now I'm going to talk about them here, mixing it with methods. So you start thinking, code and the same time probability. Okay? So suppose you have a method called X, which returns a string, head or tail. Okay? Sounds familiar, I'm sure, because you've learned probability before. Now, if the return value from X is head, the string head, okay, it always takes 1 second to execute. If the return value from the method is tail, it always takes 3 seconds to execute. Okay? Now, this method internally, it's using some kind of a random process. So I'm going to think of it as a function that involves randomization. To talk about its performance, since I know it's using randomization, I have to introduce what's called random variables into the scene. So I will use capital X to be a random variable representing the running time of one call to X. Okay? Now, since there is no bias in the method X performance, half the time I will get head and half the time I will get tail. So if I would like to use big X, the random variable big X, to represent the time, not the output, but the time it takes to call the method X, what is given to me is that half the time X is 1 second and half the time X is 3 seconds. This same kind of example, you could just read it in any intro textbook you have seen or any chapter you have read about probability, except they're not going to use, or they're not going to try to type probability with code. I'm trying to do this here. Okay? So to talk about the value of a random variable, you must be given the probability of a value and the value. So the value is 1 second and the probability of getting it is half. Or there is another value you might get, 3 seconds, and the probability of getting that is half. Okay? Now, the question is, what is the expected value of big X? The expected value of big X, we're going to call it E of X. It's the average value that we're going to get for X if we call this method an infinite number of times. Okay, so this is again a review of probability. Okay, you should have seen this stuff before, but I'm kind of refreshing your memory. And the expected value of X is a mathematical notation to talk about the value that we will get for X on average as we run to infinity. Okay, so whenever you see expected value of something, you should be thinking of what I just described. Now, to calculate E of X, what we do is we multiply the probability of the value by the value, and then we add up all the options we can get. So the probability of getting 1 is half, plus the probability of getting 3, which is half, will give me 2 second expected time. Now notice that this method will never take 3 seconds in reality. It either takes 1 second or 3 seconds. But the expected value here is an average value for a single run if we keep running this method to infinity. And we sum up all the times it took, and we divide by the amount of time, or we sum up all the number of times it ran, and we sum the number of times it ran, and we sum the total time it has run in, and then we divide this by that, and we find on average actually we're spending 2 seconds. Okay? It's important here to have a sense or an understanding of what we mean by expected value of the variable, because this is not the actual thing, it is just averaging. And the averaging we are obtaining by multiplying the value by its probability. Okay? And we will have to sum up over all choices because we don't know which choice we can get. So it's either this or that, and that's why we're adding them up. Now, suppose you have a method that has 2 calls, a call to X and a call to Y. Okay? And suppose X and Y are employing randomness. So if I would like to talk about the performance of foo, the expected value of t, where t is the time it takes to run foo, it's going to be the expected value of X plus the expected value of Y. Okay? Now, this is a very important concept that comes from the from the probability area. Okay? It's called linearity of expectation, and we use it a lot in our analysis. Okay? So the steps are, since I know that method X and method Y involve randomization, I will create a random variable for each one of them. I will create big X for the method X and big Y for the method Y. Now, since I'm interested in the expected value of running foo, so I will create also a random variable t that represents the running time of foo if we keep calling foo forever till infinity. To answer what's the expected value of t, I will sum up the expected value of x plus the expected value of y. Okay, this is what you see here. Expected value of t is equal to the expected value of x plus the expected value of y. Okay, I will compute the expected value of x separately, just like what I did before, and as well the expected value of y. Now to do that, I must be told what values or what times, how long will y take, and what's the probability of each one of those time intervals. So as you see here down at the bottom of the slide, with probability quarter, y is 2 seconds. With probability 1/4, y is 3 seconds. And the same probability, y is 6 seconds. And same probability, y is 9 seconds. Okay? So I can compute the expected value of y, which is 9 multiplied by a quarter, plus 6 multiplied by a quarter, plus 3 multiplied by a quarter, plus 2 multiplied by a quarter. I'll get some number, and that's the expected value of y, which is the average time it's going to take a run of the method y if we keep invoking it till infinity for a very long period of time. Okay, we're going to do the same. We already did that with expected value of x. The nice thing about this formulation is that this is the only place where probability comes out really clean and simple. Because the linearity of expectation is a great concept that exists in probability, because it enables us to actually solve very complex amortized or analyze very complex randomized algorithms without having to dig deep into probability theory to be able to solve what we're trying to solve. Okay, so it's a great tool for us to use. Okay, and this is what we're trying to stress here. This is called linearity of expectation, that I could sum up the expected value of a number of variables, and that will give me the expected value of a variable that encompasses all of them. So how to go about doing randomized analysis? Okay, so I've tried to list them here as steps, so you try to follow, stick to the steps as much as you can, and hopefully you progress towards a solution. The first step says that you specify a general scenario for the operation of interest, regardless of the result of the random operation being employed. What does that mean? It means don't make any assumptions about the output of the randomized process that you're using. Okay? So I'm specifying the scenario being a general scenario. In other words, you're going to roll a dice and you're going to get a value, and you don't say what the value is, and then you continue on with your analysis. Okay? Obviously, you have to consider that you're doing randomization. Like you say, I'm going to roll a dice, but I don't care about the output. Or I'm going to generate a number between 1 and 100, but I'm not going to make any assumptions about it because I'm using a fair, kind of unbiased random process, so I could get any number as output. Okay? Now, the second thing is, again, like what we did with amortized analysis, you have to identify some parameters, something to work with, or basically variables that you could manipulate and describe, using it, what's happening in the data structure or in the algorithm. Okay? The third, you're going to state your assumptions. Fourth, you're going to deduce your observations based on your assumptions. So again, this is very much like what we have seen before. We're trying to build what we call a model, to do the analysis. You don't just jump directly into trying to solve. How are you going to solve something that there is no framework to follow in your solution? Okay? When you are asked to solve something, you're following guidelines, basically. You've learned somewhere in some course. And what we're doing here is we are developing a framework through which you solve the problem. And the framework has to have assumptions. As long as your assumptions are not naive or unrealistic, you can get away with any assumption. The fourth step is you have to make some observations based on your assumption. You say, okay, if this is my assumption, then this is my observation. This is what I can conclude about what's going to happen. Okay? So we've seen this before, and we're going to follow the same approach, more or less. Now, the fifth step is we're going to create random variables. This is very important in randomized analysis. You have to work with random variables. You can't work with regular variables. So you have to create random variables, and the important thing is try to cover all the cases. Okay? All the cases means any variation you have in the code that might or might not exist should be presented as some kind of random variable. Okay? And when you actually identify or create your random variables, you have to identify the values that this random variable will take. Okay, so it's not enough to create just random variables. Say I have x, I have y, I have z. Yeah, but okay, what are the possible values of x, and what's the probability of getting any one of those values? And finally, you solve. You put the you make an equation, expected value of t, where t is the total running time, equals a bunch of expected values or expected values of random variables added up together, which is again linearity of expectation, and you solve. Okay. Now, at the end, we're not looking up for a number. If you remember from your probability course, you were asked to come up with a number. Here, we're interested in the big O notation. So we'll see how actually we can go about generating, an O of something, or an O of some asymptotic order, like O of n, O of n log n, from the expected value of t equation. So let's start our first example, hash tables. Really nice data structure because it has so many things we could use. Okay. I hope you didn't start to hate hash tables after amortized analysis, because you're going to need it now again. So my general scenario is we're going to analyze just the find. Okay. Now I need to stop here and tell you, okay, where's the randomization? Right? Because amortization, you understand from your experience with hash tables that when you resize the array that you have inside the hash table, you take it from n to 2n to 4n every time the load factor is crossed, the load factor threshold is crossed. It makes sense, yeah, we're doing amortization, but where is the randomization in hash tables? Now, it turns out actually that the hash function behavior is just like randomization. You see, you get a key, you're inserting it inside the hash table. What do you do if you're not going to resize the array? You just pass it to the hash function, and the hash function is going to give you as output an index, which is an index in the array. Okay? You could just as well roll a dice between 0 and n-1 and get some index and insert the key in the array. Now you might tell me, oh yeah, but that's not exactly like the hash function, because the hash function is behaving in a specific way to introduce sprinkling of the values or of the keys within the array cells, and it's taking mod of the array size. Well, we can get the same effect of mod by generating a number between 0 and n-1, but yeah, with the random number generation, we will not have sprinkling effect. You just have randomization, and that's it. But actually, if you think of it, there is a lot of resemblance between the way hash functions work and any random function works. You give it an input, and it's going to give you a value between 0 and n-1. Okay, that's in the case of the hash function. You could also think of a randomization process that you pass it some input, and it's going to give you an output between 0 and n-1. So the randomization part in the hash table is actually the hashing itself. The hashing function itself is behaving like a random function. Okay? Now, we need to analyze the effect of using hashing on the data structure to really claim that it's O of 1. Okay? Because what if all the entries we pass to the hash table when we are inserting, we're doing a put, they will all go to the same cell. Then we'll have lots of collisions, and it will turn to be basically a linked list if you're using chaining. But the question is, can we get that? And the answer is no, because if you use even a half decent hash function, you will get some sprinkling. You will get the values thrown around in different cells in the array, and that's precisely some kind of a random behavior, if you like. Okay, it looks like random behavior. It is some kind of random behavior, so it involves randomization in that sense. Okay, so my general scenario is I'm going to just analyze the find. Why? Because the find is simple and nice. It only has the hashing part, and really I'm interested in the hashing part. I'm not interested now in the resizing of the array from n to 2n to so on, or the halving of the array from n to half n, because that will happen in the put and in the get. But I don't want to go there. I just want to focus on the hashing, because this is really the randomization part. And the method that has just the hashing is the find. So I'm just going to analyze the find. Okay? And whatever I find from the find, whatever I reach to as a conclusion about the performance in the find is applicable to the insert and is applicable to the get, to the put and the get in the hash table, because over there I also use the hash function. Okay, so we're going to use the find to do the analysis. Now, my general scenario is the key hashes to bucket B. I got a key, I'm going to hash it to some bucket B. Okay. Now, what are my parameters? I'm going to use the same parameters we discussed before. I have big N, which is the number of buckets, small n, which is the number of items, and L, which is the load factor, small n by big N. That's pretty much everything I can work with in a hash table. So here is my assumptions. I have a random hash code, okay, which means I'm using a decent hashing function that will randomly pick some cell to put the value in. Okay. I'm also assuming that the hash table is using chaining. So if I get collisions, I'm going to put them in the chain. I will ignore the case for duplicates. Okay. I just don't want to complicate the analysis, and there are actually a lot of hash tables who don't have duplicates. The duplicate value will replace, or the new value will replace the old value, and there is no duplicates. There's no support for duplicates. Okay, because duplicates always create problems for us. So if you'd like to support it in your hash table, if you're building a hash table from scratch, this is just because you would like to give the programmer some flexibility. But really, he's not going to get a good all-in-one performance if all his data is duplicates of each other. Okay. And I will assume there are n keys in the table beside k. Okay, so I'm basically considering a general scenario. There are some values in the hash table, and k will go to some bucket B. Okay, I'm trying again to build a model here to be able to do the analysis, to be able to come up with a finding that says, the find is going to be O of 1 randomized. Okay, so to have a decent scenario to analyze, I'm not going to claim that, oh, this is the first entry that goes into the hash table, because if this is the first entry that goes into the hash table, there is nothing in the hash table, you don't have collisions, you have nothing, you will go to any cell and look up that value, okay, if you're doing a find. So I will assume there are some keys already there, okay, and I'm using a random hash code, so it's going to spread them around in the hash table properly, okay. Now, let's build some observations, and here the observations must start to rely on probability, because we're doing randomized analysis. So, here is my first observation. Since we have n buckets, big N buckets, okay, each key has a probability of 1 over big N of hashing to some bucket, okay. So again, the observations you must now start to get probability involved in the picture. So my observation, according to my relatively simple model here, is that if I'm saying I have n buckets, and the bucket is the destination that I put the key in, any key I have, okay, has a probability of 1 over big N, okay, to go to basically one of the buckets. So if I get key 10 and I have 5 buckets, the probability of key 10 to go to bucket number 1 is 1 over 5. The probability of key 10 to go to bucket number 2 is 1 over 5. The probability of key 10 to go to bucket number 3 is 1 over 5. Why? Because I have 5 buckets. So since I'm picking any one of them randomly, so the chance of going to any one of those buckets is just 1 over total number of buckets. Now let's do the analysis. In the analysis part, I start introducing random variables. Okay? Now, and I say random variable, it's not random variable, okay? I for sure will have a random variable, we will typically call it t, which is the expected time to run find, okay? Or t represents the time to run find, and the expected value of t is what I'm going to compute. But I don't want to jump directly. Yeah, when you're solving such a problem, you can start by saying, okay, I have t, which is the random variable that represents the amount of time it takes to run the method find. But this is not the only one we're going to work with. We're going to introduce random variables, as many as we like, really here, okay? It's a random variables here are introduced associated with probabilistic events. So you have to look at the problem or given problem and understand where are the probabilistic events. Now here I have many keys, and each one of those keys has a probability of getting or for falling into a specific bucket. So I will introduce a random variable for every key. Okay, this is what the first point says. I will set up a random variable for each key in the table. So random variable 1 for key number 1, random variable 2 for key number 2, random variable 3 for key number 3, all the way to random variable n for key number n. Okay? Now once I start to introduce random variables, I have to start thinking of the values for those random variables. Okay? And this is what the second point is trying to handle. It says for each key, k sub I, okay, v sub I, or random variable that's represented, is equal to 1 if the key hashes to bucket B. Else, v sub I is equal to 0. Okay? Now, why am I interested in this bucket B? Because in my initial model, I'm assuming that I'm going to find a key that hashes to bucket B. Now, I want to know how much time I'm going to spend trying to find that key, K, in bucket B. And that is related to the elements or the values that already exist in bucket B. So another way to ask the question, what's the probability of seeing something in bucket B? Okay? Because again, this is probability. They will be thrown all over the place based on some random fashion. So when I talk about a specific bucket, let's say the third bucket out of a list of 10 buckets, and I'm going to go and search in the third bucket because this is the output of the hashing function. It's taking me to the third bucket to look up for a specific value, let's say 55. The question is how much time I'm going to spend searching for the value of 55 in bucket number 3. Now, probabilistically, to answer this question, we basically are asking what's the probability for every one of our keys that exist in all of this hash table to fall in bucket number 3. Okay? If it does fall in bucket number 3, I'm gonna say that v sub I, the random variable associated with it, is equal to 1. If it doesn't, it's going to be 0. Okay? So the cost of finding k, which is 55, in bucket number 3, okay, is what? I'm going to hash k. So there will be a cost for that. I will, since this is a mathematical computation, I will say the cost is just 1. It's a constant. Okay, it can be any constant, but let's say it's a 1. Plus v1 plus v2 plus v3 plus vn. That's the cost of finding k, the cost of running the method k, where v1 represents the chance of having or finding the first value in bucket B, plus v2, which is the chance of finding the second value in bucket B, which is bucket 3, plus v3 all the way till vn. This is just the random variable equation, which is t equal to 1 plus v1 plus v2 plus v3 plus vn. Okay? But what I'm interested in is the expected time on average as we go to infinity. So I'm going to take the expected value of each one of those random variables. Okay? So I will say the expected value of t is 1 plus the expected value of v1 plus the expected value of v2 plus the expected value of v3 all the way to the expected value of vn. Again, let's start from the beginning. I'm creating random variables. I'm introducing into my model where I built the analysis random variables. The random variables have to be chosen wisely. The criteria is whenever you see a probabilistic event, which is could happen or could not happen, or there's a chance of this happening by this much versus something else happening to that same thing but by some other value, okay, by some other percentage, you introduce a random variable. Since what we are talking about here are keys in a hash table, I'm going to create a key for, a random variable for every key in the hash table. Okay? You cannot just create random variables and stop. You have to say the value. You have to come up with a value. And here it depends really on what the random variable is representing. And I'm choosing here the random variable to represent its existence or not existence in a specific bucket I'm interested in that I'm going to analyze the find on, which is bucket B. Let's say it's bucket 3 again. Okay? So If a specific random variable exists in bucket 3, the value of the random variable, sorry, no, I'm getting confused. If a specific key exists in bucket number 3, I'm going to assign its random variable 1, which means it does exist in this bucket, else it's 0. Okay? So the total time to run a find is do the hash plus go and check on each one of the keys that exist in this bucket. And this is what t equal to 1 plus v1 plus v3 plus v2 plus all the way till vn means. Okay, go and check, make an equality check. Let's say you're looking for 55. The first key is 100. If the first key, which is 100, exists in bucket number 3, you're going to compare 55 with 100 to find out that 55 is not equal to 100, then you go to the next one. But if 100 does not exist in bucket number 3, you're not going to do this comparison. So it's a matter of chance whether 100 exists in bucket number 3 or not. And this is why I would represent its presence in bucket number 3 as a chance, as a probability. And this is why I'm using a random variable. Okay? So each one of those random variables from v1 to vn is representing the chance of actually having that value that corresponds to this random variable in the bucket I'm currently searching in, which is bucket number 3, just by accident. This is the output of the hashing function, just bucket number 3. I passed 55 to the hash function, I got the index 3, so it's bucket number 3. Okay? Now, I'm interested in the average time the find will take, because I'm talking now about a specific scenario where 55 in bucket number 3, but I want to compute that for all buckets, for all finds that I will ever run. So I have to take the expected value of t to really be the average that I'm looking for. This is really the average I'm looking for. So according to linearity of expectation, I can just introduce the expected value notation on all the random variables, and this is the formula you see at the bottom. Okay? So now we solve. Once you reach to expected value of t and a formulation, you are way ahead in your analysis. Okay? Now we solve. I would like to find the expected value of v1, the expected value of v2, the expected value of v3, and so on. Because if I can find a value for each one of those guys, then I'm done. Okay? So we have to work out what's the expected value of v sub I. Well, we know we have big N buckets. So the expected value of v sub I is 1 over big N. Because if I'm asking, what's the chance of the value 100? We said this is the first value in our hash table that we ever inserted. What's the chance of the value 100 appearing in bucket number 3? Well, if we have 10 buckets, it could go to bucket number 1, it could go to bucket number 2, could go bucket number 3, could go to bucket number 4, all the way to bucket number 10. It has a fair chance to go to anywhere. So if I ask, what's the chance of 100 to go to bucket number 3? It's 1 over 10. It's 1 over the number of buckets. Okay? So E of V1 is 1 over N. The same thing for the rest. E of V sub 2 is 1 over N. E of V sub 3 is 1 over N. Okay? So in total, the expected value of T is 1 plus small n by big N. Okay? It's 1 plus small n by big N. I'm just summing up all of those 1 over n's. How many 1 over n's I will have? I will have n of them because I have n keys in the hash table. Okay? So it's 1 over n plus 1 over n plus 1 over n, small n times, so it's n divided by small n divided by big N. Okay? So this is the expected value of t. But here's the interesting thing. Look at small n by big N. What is this? This is the load factor. Okay? Now, in a real implementation of a hash table, the small n will be an actual number, not a variable, an actual number, say 10. And big N will also be an actual number, say 20. Okay? So it's going to be 1 plus 10 divided by 20, for example. If you'd like to solve this, the expected value of t. Okay? So you can actually replace the small n and big N for any run with actual values. And what that means, the expected value of t is going to be a number, which means it's a constant. It does not contain a variable. You got the idea? This is why we say that the hashing mechanism, as long as in the hash table the load factor is respected, okay, which is the ratio of small n by big N, that you keep resizing. The defined hash function is O of 1. It's a constant. It's not 1 per se as in 1. It could be any number, but the point is it's a number. It's not a variable. And that's what you see here in A of t at the far right side. It's 1 plus some number that represents the current number of entries in the hash table divided by the number of buckets in the hash table. And both of these will be actual numbers. So 1 plus some fraction, okay? And that will give you a constant. So we've just proven that, according to our model here, as long as there is no bias, which means there is a tendency to send certain inputs to certain buckets, so you start getting lots and lots of chains. As long as you're using a good hashing function, you will be going for a constant number in terms of the expected time to run a find or the hashing process. And this same hashing mechanism exists in the put and the get, so we will say it's O of 1, it's a constant. Let's look at the next example, which is quicksort, which we have spent some time while discussing divide and conquer, analyzing how it works. The randomized behavior in quicksort is that when it picks a pivot, it's rolling a dice that generates a random number between 0 and n minus 1, and that output is actually the index of the pivot. Okay? And afterwards, it's the same technique we described earlier with quicksort. Once we pick a pivot, we will make sure that all values appearing to the left of the pivot is less than the pivot, and then all values to the right of the pivot is greater than the pivot. And then that will only mean that we have accumulated values that are less than to the left and greater than to the right, but that doesn't mean that the ones to the left are sorted or the ones to the right are already sorted. So we do the same technique again and pick the left alone, pick a random variable between 0 and the pivot index minus 1 and pivot index plus 1, and then for the right side and until the end of the array we pick a pivot in that range, and we keep doing the same process recursively as we discussed earlier. Okay? Now, the thing is, quicksort relies heavily on picking the pivot randomly, and it's the best choice. Okay? It's the best choice. So let's study why it's the best choice. So by the way, before I move on, what do I mean by it's the best choice? Because there are other choices. For example, you could tell me, oh, what about just picking the element in the middle, and instead of generating a random pivot location, why don't I just always find the size of the array, divide by 2, and work on the element in the middle? Or what about if I just pick the first one to the left, or the last one to the right, and make it the pivot? Okay? So it turns out actually that the best case is to use a pivot that is randomly generated. So let's look at the analysis of quicksort. The general scenario that I will try to analyze is the partitioning due to a pivot location that was generated via a random process. So what we're basically doing all the time in quicksort is we roll a dice where we generate a random number between 0 and n minus 1. We get the index of the pivot, and then we proceed to partition the array into two sub-arrays, left of the pivot and right of the pivot. Since randomization is involved in this pivot index generation, I will study the impact of this random process. Consequently, I will study the partition, because this is the step in the algorithm where the randomness plays a role in, or the step that the randomness output or the random output affects. So in terms of parameters I can talk about, or I could use in this context, first of all, x, the pivot selected, okay, the pivot itself, I'm going to call it x, n, the number of elements in the array, and s being the size of n, the size of the array. So I am parameters, to build a model to start the analysis is the pivot, the array, and the array size, and as well as L and G, the left subarray, left of the pivot I mean, and G, the right subarray of the pivot. And L and G refers to less than the pivot and greater than the pivot. So what are my assumptions here? I will assume that the keys that have been inserted into the array, the values I am sorting, do not have bias in them. Okay, so the chance of getting any value is the same as the chance of getting any other value. I don't have clustering of values, they are uniformly distributed. So if the smallest number is 1 and the largest number is 20, and I have 5 values in the array, I will assume that they are uniformly distributed in the space between 1 and 20. Okay? And again, I don't have bias, so all permutations are equally likely. Okay? So this is an important assumption because if you know something about the input, then you could perhaps select some other sorting technique. But if the chance of getting a value is the same as the chance of getting any other value, then you're really talking about the general case, where you can get any input, basically. And that's what I'm saying here in my assumption. It's going to be for any input, not a special input designed to defeat quicksort, or a special input that the data is not necessarily designed to defeat quicksort, but the data has a certain pattern that it exhibits all the time. Okay, like for example, numbers that continuously increase and then suddenly continuously decrease and then continuously increase and decrease. Okay, so I don't have any pattern in the data. Even though with such patterns, even quicksort will still win if we use randomness. But I'm assuming here the general case, which is that the data, there's no bias in them, there's no design in them, they're just random data. Okay, and I will assume random pivot selection, obviously. And a very fundamental issue here that I try to hint to in the last point in this slide is that we are going to turn pessimistic cases into good cases by picking the pivot randomly. Okay, so the reason why randomness works here so nicely compared to any other technique you could think of, including picking the element at the middle or the first element or the last element, since you're going to land anywhere in the array while you're actually picking a pivot, any worst case scenario, while you might see it in one iteration of quicksort, the next iteration, while you're sorting a set of items or a set of numbers, that worst case will not be faced because you're going to go somewhere else because of the randomness. And this point will become clearer as we progress in the explanation. So what are my observations? Well, if you think of a set of numbers and you're rolling a dice to get a value between 0 and n minus 1, and that is going to be your pivot, ideally, what do you want? What you want is to get a pivot value who is in the middle of the sorted equivalent sequence of your array. And let's say I get a bunch of numbers between 1 and 20. I have 10 numbers between 1 and 20. If I sort them, the number in the middle, say, is 11. I will be really lucky if I roll a dice and I get an index where the 11 is stored. Because if the number in the middle is 11 and I pick that as my index, I mean in the middle in the sorted sequence of values, but the values are not sorted, so I don't know that number. It's not easy to find that number unless I sort the array, and I'm starting with an unsorted array, so it's not easy actually to find the number in the middle. But if by accident I get a pivot index whose value is the 11, okay, the cell value that's stored in the array is 11, that's like a perfect ideal scenario, because this means when I actually go about creating the L and G subsets, the left and right of the pivot, half the elements will fall to the left and half the elements will fall to the right. Okay? And this is perfect division. This is the ideal case. So if I get 20 values, I will have one array to the left that has 9 and the other one to the right will have 11 or 10. Okay? And the pivot is in the middle. That's ideal because I've split them to 2 equal subarrays. Now, obviously, there's no guarantee that we are going to get an index who will create a perfect split in the array we're trying to sort. Now, why are we interested in getting this perfect split or in have equal subarrays coming out from the division after picking the pivot? Because if we keep doing that, we're going to get the nice log n, which is what we are after. Okay? In terms of the height of the tree. Now, the problem is there's no guarantee what you're going to get. So we're going to think of the good and bad scenarios. What's a bad scenario? The bad scenario is you roll a dice, or you generate a number between 0 and n minus 1, and the index that comes out is actually the index of the smallest element. That's really ugly, and you're really unlucky, because this means you will create 2 subarrays. One is empty of size 0, and the other one has the rest of the elements. Okay? So there are 2 extreme cases. A best case where we split the array into exactly 2 equal halves, and a worst case where we split the array into 0 subarray and the rest in the other subarray. So the L will be 0 in terms of its items, in terms of the number of values in the L subset or the L subarray, and G will have all the other values in the array. Or the reverse, G will be 0, there will be nothing there, and L will have all the other values in the array. And that will happen if you pick the minimum number in the array, the smallest value in the array, or the largest number in the array. So now we have 2 really bad cases. The rolling a dice or generating a random number makes you pick the pivot to being the smallest value or the largest value. In both cases, you're really in a bad shape. And we have an ideal case where you pick the value that will split the array into 2 equal halves. Now, do we have other cases? Yes, we're going to expand a little bit our understanding of what's a good case to think of all the values in the middle of the sorted sequence of the entries in the array, of the values in the array, the values in the middle, to be all good cases. And the first quarter to the left and the last quarter to the right, which will make the other half, are bad cases. Okay? This is what I try to highlight in this slide. That the best case, the partition will split the array into 2 subarrays, each of size n by 2. The worst case, partition splits the array into 2 subarrays, 1 and n minus 1. Okay? Now, the thing is, you have no control. So you are going to get a mix of good and bad situations, or a mix of good and bad pivot selections. Sometimes you roll a dice, you get a perfect pivot. You're splitting the array you're working with into 2 equal halves. And sometimes you will roll a dice and generate the random number you're after, and you will get the smallest value picked or the largest value picked. And that's a bad case. Okay? And this is what I try to highlight here. On a random input array, we will have a mix of well-balanced and unbalanced splits. Good and bad splits are randomly distributed across throughout the tree. Okay? The tree of sorting the array from beginning to end, we will have good splits followed by bad splits, followed by good splits, followed by bad splits, and so on. And this is what I try to highlight here. When I'm referring to a good split that shows up, this is the figure, I'm referring to the figure that appears in the right, the figure that appears to the right. I have a good split. I end up with 2 balanced, almost balanced subarrays. On the figure on the left, as you see, I split it first to 1 and n minus 1. So I have an array of n, and I split it into an array of size 1, and the other array had n minus 1 entries. But the nice thing is, this n minus 1, even though it's horrible, because if I continue getting n minus 1, I will end up with a linked list, and it's going to be a skewed tree. This n minus 1, even though it's a bad split, when I roll the dice the next time, the chance is I'm going to get a good split. So I will divide that into 2 equal halves. Okay? So I could start by getting a good split and then find myself getting bad splits later on, or I could start by doing a bad split and then find myself doing a good split afterwards. So again, to stress the point, the worst case for quicksort will occur if the pivot is the unique minimum or maximum element. So either L will be empty and G has the rest of the elements, n minus 1, or G will be empty and L will have n minus 1 elements. And the other one that's remaining from the list is actually the pivot itself. Now, the running time of this obviously is going to be n squared. It's going to be processing n, then processing all of n minus 1, then processing all of n minus 2, then processing n minus 3. I mean by processing here is picking the pivot and dividing to L and G, and again you end up with one of them empty and the other one has the rest of the elements. Okay? So you solve this, n plus n minus 1 plus n minus 2 all the way till 1, and then you get n squared. Okay? And the tree on the bottom right shows this idea that you're doing this way n squared effort, because you start with the whole array and then you pick a pivot that happens to be the minimum, so you get all of the values on the right side, and then or on the G subarray, and the L is empty, and that keeps repeating all the way till the end. By the way, if you pick the pivot with a different strategy, for example, if you pick the pivot to be the first element to the left, you will immediately run into this scenario if the numbers are in increasing order. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you pick the first one as the pivot, it's 1. So you'll end up with an empty L, and the G will have from 2 to 10. And then you go again and pick the first element to the left, or the first element in the subarray you're working with, to be the pivot. So you pick to 2. And then again the L will be empty, and the G will have 3 to 10. And then again you go and pick in the next iteration or the next invocation of the algorithm, you pick again the first element to the left, and again you go into the same scenario. You're going to have the 3 alone, and then 4 to 10 in the 3 is the pivot, the L is empty, and 4 to 10 is in G. Okay? Similarly, if you pick the rightmost element and you get a sequence of increasing values or decreasing values, and again you're going to have L full, or decreased by 1, and G is empty, or depending on you have an increasing or decreasing sequence of values in the array that you're starting with, you will have the reverse, where L is empty and G is full, or have n minus 1. So picking the first and the last will fail to give you good performance if you consistently do that. And this is why we avoid picking the first element as the pivot or the last element and the pivot, and we prefer to pick it randomly. Similarly, if you pick the number in the middle, you run into a trouble with certain patterns of data. I mean by pick the number in the middle, what you studied in the case of binary search. You find the length of the array or subarray you're working with, find the value in the middle, and try to split on the value in the middle. So there are data patterns. Let's think about that together. Which data pattern will exist where the number in the middle will completely fail you? You will end up with O of n squared performance. If you have actually a pattern of continuously increasing numbers and then suddenly they decrease at the middle, and then again continuously increasing numbers. So actually the smallest number is in the middle. Okay, so they start from a small value, and then they keep increasing, and then they sharply decrease, okay, until they hit a bottom, and then they increase again. It's almost like a sine wave that goes up and down. So when you pick the value in the middle, you will pick the smallest value, and then when you split, all the values will be greater than it, so G will be full with n minus 1 items, and L will be empty. So again, picking the value in the middle is not a good idea. So neither picking the value in the middle is a good idea, neither picking the value, or basically it will not work all the time, that's what I mean. Neither picking the first element is a good idea, it will not work all the time. And similarly, picking the last value in the array is also, is also not a good idea, because you will fail sometimes, and the performance will regress to O of n squared. Okay, so I hope this idea is clear now. Why are we doing randomness? Now let's go back to the issue of what is a good call and what's a bad call. Okay, now here is the thing. We are going to expand our understanding of a good call. There is good and there is ideal. Ideal or perfect is you get exactly the value that lies in the middle in the sorted sequence, or the sorted version of the array that you're trying to sort. Okay, so look at the array that exists at the bottom of the slide. When I start, I'm not getting the values sorted like this. I will get the values all mingled together. So they might be like, 2, 7, 8, 9, 1, 13, 15, 16, 11, 12, 7, 8, 6, 5, 1, 3, and so on, okay? They are intermingled together. Now, let's imagine that I take them onto the side and I sort them. Now, obviously, we're not going to be doing that, because if we do that, then there's no point in quick sort. But let's imagine we took them and then we sort them. And then let's look at them. Now they are sorted, okay? Anywhere in the yellow region in the middle is a nice value to pick as a pivot. Ideally, you would want the 8 or the 9, because the 9 will give you very nice split, two equal subarrays. But not only the 8 and the 9, the same thing for the 7 and the 5 and the 6 and the 11 and the 12. Okay? We will expand our understanding basically by saying that if I get a pivot in on any one of those values, if the random process I'm using will produce an index that will be for any one of those values in the array, okay, regardless where they are, any one of those values, the outcome is going to be good. Why? Because the sizes of L and G are each less than 3/4 of the input. Okay? Ideally, 9 will give you half and half. 10 will give you, let's count them, 1, 2, 3, 4, 5, 6 on the right side, and so let's count it again. If I get 10 as the pivot, 1, 2, 3, 4, 5, 6 on the right, and 1, 2, 3, 4, 5, 6, 7, 8, 9 on the left. They're still good, okay? They're close. So it turns out actually that anywhere in the yellow region will give me not necessarily equal split, but acceptable split. A good split, we will call it, okay? The criteria is 3/4. That each of L and G is less than 3/4, okay? Or it should be really either L and G is less than 3/4 and the other one will have the rest. But I'm talking here, in English terms, L and G are each less than 3/4, okay? Now, anywhere where it's in blue, the background is in blue, which includes the 1, the 2, the 3, the 4, the 13, the 14, the 15, and 16. Any one of those values is really bad, because the L or the G will be more than the 3/4. For example, if I get the 15, I will have the G having 16 alone, and the L will have the rest from 1 to 14. If I get 13, I will have the G having 14, 15, 16, and the L will have the rest from 1 to 12. Okay? So there are good pivots and there are bad pivots. Okay? And I tried to show that with the illustration that appears in the middle of the slide. A good call is a call that enables us to pick, which is again going to be happen by accident because this is randomization, that will enable us to pick one of the values that appear in the middle of the sorted version of the array. Okay? The middle 50%, or the middle half. Bad calls are going to be based on accessing a pivot who will create a split where one of the L or G is much larger than the other one. Now, one thing to realize here, the number of good pivots is equal to the number of bad pivots. Even though the bad pivots resides on the periphery of the array, if you count the entries, actually it's half and half. The half in the middle is good, and the quarter at the beginning and the quarter at the end are bad. So basically half is bad and half is good. So the probability of making a good pivot, of getting a good pivot from a random selection is 50% of the time, or half. Okay? And the probability of getting a bad pivot is also 50% of the time, based on our model here. So I'm going to solve with you the analysis step in two ways. I'm going to show you the informal, kind of intuitive way to reach to a conclusion about the performance, and I will also show you the formal way. Okay? Now, to go about the informal one, we will have to use this probabilistic fact that states that the number of coin tosses that you are required to make to get k heads is 2k. What is this saying? It's saying that if I give you a coin that has a head and a tail, okay, or as we say in Arabic, malik or kitaba, to get a certain number of one of those two variations, malik or kitaba or head and tail, you have to toss the coin up in air 2k times, where k is the number you are interested to get. So if you'd like to get 10 heads or 10 malik, then you have to toss it in the air 20 times on average to get the 10 heads. Okay? The other 10 is going to be the other side of the coin, the other face of the coin. Okay? Now, this is something we will use now. Now, let me read the second point. It says, for any node in the tree at depth I, what do we expect? We are saying half the time we're getting good pivots, and half the time we're getting bad pivots. So for any specific node, anywhere you pick in the tree, okay, which tree I'm referring to here? I'm referring to the tree of sorting the array. So I start at the root with the array not sorted, and then I pick a pivot and I split it to two sub-arrays, so I'm going to put it as children of the root. And then again, for each one of those sub-arrays, I roll a dice, I pick a pivot, and I split that further to two sub-arrays, so again I'm going to connect it to the children of the root. So this will be the grandchildren of the root, and it keeps like this until I hit the base case at the bottom of the tree. So for any one of those nodes, I will arrive to it, or by the time I reach to it, I must have seen half the time good pivots and half the time bad pivots. And this is what this is saying. For any node in the tree at depth I away from the root, I by two ancestors are good calls, which means good pivot selection. Okay? And I by two are bad. Makes sense, right? This is according to what we have been discussing. The chance of good pivots is equal to the chance of bad pivots. It's half and half. So if I have rolled the dice 6 times, because I moved down 6 levels from the root, 3 times I got good pivots and 3 times I got bad pivots. Okay? So for that specific node I am standing at, the size of the elements inside it, or the size of the sub-array inside that node that I will be splitting later on, but I'm just talking about that specific node at that specific instance, will be at most 3/4 to the power of I divided by 2 multiplied by n. And the question is, why? How can we actually get this number? Now, first thing is, it has to be a fraction of n, and what you will end up with getting here to the left side of n is some kind of a fraction. which makes sense because you start with n and you're splitting it into equal halves, in the good case almost equal halves, and you keep doing that. So if you start with an array of 100 and 6 levels down in the tree of splits, you're not going to have n being equal to 100. It's going to be a fraction of the 100. So it makes sense to multiply that by n. But why am I doing 3/4 to the power of I divided by 2? Okay? So again, the question is, why 3 divided by 4 I to the power of 2 multiplied by n? What I'm interested to get here is the largest size that n could be, n at that specific node I am processing anywhere in the tree. If I assume that I have seen 3 out of the 6, if we're saying we are at level 6 down from the root, then we have seen 3 bad ones and 3 good ones. The 3 bad ones, the 3 bad pivot selections, each one will result in 3/4 and 1/4. We said this is really the bad scenario, where the majority of the elements will go in one side and the other side will have just a minority of the elements. So 3/4 is the worst case. 3/4 and 1/4 on average is the worst case. Split is the worst case split. I would have seen that 3 times. Out of the 6, 3 good pivots, 3 bad pivots. 3 good pivot selection, 3 bad pivot selection. Each one of the 3 bad pivot selections resulted in 1/4 and 3/4. So in total I would have seen 3/4 and then a good pivot, and then 3/4 and a good pivot, and then 3/4 and a good pivot in the worst case, because I'm assuming that the 3/4 will rely on the same access or the same path to my current node from the root, which is not entirely true. I mean, it could be that I got 3/4 and a 1/4, but actually the side I am on had a 1/4 at one of its parents. But I will assume the worst case, which is that I got 3 bad pivot selections, and in each one I got a 1/4 and a 3/4, and the 3/4 were on the path from the node I'm at to the root. So how many times I got the bad 3/4? 3 times out of the 6, and that's why I am raising this to the power of I divided by 2, where I is the depth. So if it's 6 and 6 divided by 2, so it's 3. So 3/4 multiplied by 3/4 multiplied by 3/4. That's the worst case. We're quite unlucky, okay? We're quite unlucky not in getting 3 bad pivot selections. We're quite unlucky because when we got the 3 bad pivot selections, the 3/4, which is the majority of the elements, resided on the side that actually we're traversing down to my current node I'm standing at. Okay? This is the explanation of why this is at most 3/4 to the power of I divided by 2 multiplied by n. So what I have found from the previous slide is that the n node, which is the size of the current subarray I am working with at any level in the tree, is going to be at most equal to 3/4 to the power of I divided by 2, where I is the depth of this node, multiplied by n. Well, that's interesting. Let's actually look at the leaf level, which we have to reach to in quicksort, which is the base case at which we do nothing because there is nothing to be done. Now at the base case, n node in the top right equation that I have highlighted in a red rectangle, n node will be 1. So if I actually plug in 1 here instead of n node, what would be the I? To solve that, we will have to take the log. Okay? And that's what you see as the point that says for a node of depth 2 multiplied by log 4 divided by 3, log to the base of 4 divided by 3n, the expected input size is 1. So again, I'm doing here a straightforward logarithmic manipulation. I have figured out how many at most elements I would have at every level in this tree of subarrays, starting from the root where I have the whole array, and then the next child or left and right children will have the two subarrays splitted from the root or derived from the root by picking a pivot, and so on. So I have a formulation of the number of elements that exist at most in any one of those nodes, which is 3 divided by 4 to the power of I divided by 2n. It's a fraction of the n. And as the I increases, the fraction of the n decreases because I keep splitting. Now, if I set my n not equal to 1, which means I know that I actually have 1, where do I'm sure I will ultimately have 1 at the leaf level. Why this is interesting? Because I want to know the height of this tree. How many times I'm going to split. So if I set my n not equal to 1 and I solve, I will find that I solve for n, I will find that the height of this tree is log n. Because if I set 1 equal to 3/4 divided to the power of I divided by 2n, and I would like to express or find the height of the tree, I have to apply the log, and this will tell me that the height of this tree, the h, is equal to O of log n. So the height of this tree is O of log n. But when we're actually doing the creation of L and G, which is after picking a pivot, I have to create L and put in it all values less than the pivot, and G and put in it all values greater than the pivot. Every time I am actually doing that, I am doing O of n work. I'm processing all the elements I have on every level from left to right to decide whether they should go to the L or the G. How many times I'm doing that? I'm doing that log n. So in total I'm doing n log n. Okay? And this is expected. Why? Because every time we run the algorithm on the same input, we're going to see a slightly different tree because of the effect of randomization and generating random numbers. Okay? So unlike the deterministic sorting techniques like selection sort and insertion sort and merge sort and bubble sort, those ones are deterministic. If you pass the same input, you're going to see exactly the same tree produced. It's going to be exactly the same steps because it's exactly the same code. But here we're having a random factor, which is every time we roll a dice to figure out which pivot to pick. What that means is for the same input, this tree of divisions of the input array is going to change slightly. It's not going to be always the same. It's going to change from one run to another. But what is interesting is that it will always be of height log n, and we're always doing n processing in every level, which means it's an expected running time of n log n. Now that's the informal way of thinking about it. Let's see the formal way. Okay? The formal way, we go back to what I described to you earlier. I would like to calculate the expected time to run quicksort on a set of n values. Okay? How do we actually go about that? The expected time to run quicksort on n values is equal to the chance of getting a bad pivot multiplied by the cost of getting a bad pivot, plus the chance of getting a good pivot multiplied by the cost of getting a good pivot. Okay? We said that's half and half, by the way. We already figured that out. Plus the chance of comparing elements. Okay? So the math here is going to be very detailed. If I go and do the exact what I did in the informal analysis, which is to consider the pivots being half in the middle good and 1/4 bad at the beginning and 1/4 bad at the end. I'm just going to simplify it, but I'm sure once you get the basic idea, the extension of or redoing it for the more general case is going to be relatively straightforward. So let's see first the simple case of going about this, or the simple approach to do it formally. So I will work with two bad scenarios, picking the maximum and the minimum, while everything else is good. And again, the changes is not going to be drastic from what I'm going to show you if we work it with half good and half bad. Okay? So here again, I'm gonna calculate my expected running time based on only two bad scenarios, minimum and maximum, because it will produce to me a skewed list or a skewed array, and everything else is good. So let's see the analysis. So this is the analysis, okay? The quick sort, I will read it line by line, and you will have the solution also available online. The quick sort of n is equal to the quick sort of q plus the quick sort of n minus q plus some processing of the array to actually create the LNG. Okay? Why it's written like that, quick sort of q plus quick sort of n minus q, this is actually what we do when we pick a pivot. I pick a pivot, I create the LNG. The L has all the elements less than the pivot. The G has all the elements greater than the pivot. This exercise I'm just describing is what is described here as, the theta of n. That we are going to do this for sure, okay, to create the LNG. But what do we do next? We're going to call quicksort again on L and quicksort again on G, and check the code that I have showed you earlier on when we discussed divide and conquer. This is how we proceeded in quicksort. I create L and G after picking the pivot, and then I call quicksort on L and quicksort on G. So this is what I'm trying to encode here. I'm saying that the quicksort of n is basically the quicksort of q, you could think of this as L, and the quicksort of n minus q, which you could think of this as G, plus the creation of L and G, which is the theta of n. This is the first line. Okay? Now, I will apply immediately the expected value notation. So this is, expected value of quicksort of n is the expected value of quicksort of q plus the quicksort of n minus q plus the expected value of theta of n. Theta of n is deterministic. There is no randomization there. So if you look at the third line, the expected value of theta of n became just theta of n because there is no randomization, okay? There's no different chances. You're going to pass through the elements from beginning to end, whether you like it or not, basically. So you got to do this processing, so there is no notion of what's the chance of doing it. The chance is 100%, so you're going to do it. So it's theta of n, okay? Now, the remainder part of the third line is still the expected value of q of s of q plus q quicksort of n minus q. So this is the part I'm going to work on. After the plus sign will remain with us all the way till the end, as you see in the last line. So now we really need to work on quicksort of q plus quicksort of n minus q, the expected value of that. I said we have here two bad cases, picking the minimum, picking the maximum. So I'm going to talk about them that way. It's 2 multiplied by 1 over n. 1 over n is the chance of picking the minimum or the chance of picking the maximum. So if you like, it could be said like 1 over n plus 1 over n, but I'm just going to write it 2 multiplied by 1 over n. Multiplied by the quicksort of 1 plus the quicksort of n minus 1, because when I get the bad element, the bad pivot, which is the minimum or the maximum, it's going to be generating to me an L that has 1 and a G that has n minus 1, or an L that has n minus 1 and G that has a 1. And this is what I'm trying to encode here, okay? It's a chance of doing that. What's the chance of doing that? It's 1 over n, or getting that, it's 1 over n, okay? And I have 2 of them, that's why it's 2 multiplied by 1 over n. So that's the chance of getting the bad pivot. Plus, let's actually work out the chance of getting the good pivots. What's the chance of getting any good pivot? It's 1 over n. Okay? Now, but 1 over n, I have the rest. 1 over n of the rest. Okay? The rest include all but the smallest and the largest. So that's going to be from q equal to 2 until n minus 1. What am I going to do? I'm going to do quicksort on q plus quicksort on n minus q. Okay? Now, what remains in this analysis is just working out the mass. Okay? So, in the next line, I take one of the 1 over n's and put it inside the summation to just make it 1 over n. That's why you see the q changes to q equal to 1 instead of q equal to 2. Okay? And now I will try to resolve. The quick sort on 1 is obviously it's in theta of 1 because there is no effort to sort an element by itself. The quick sort of n minus 1 will ultimately, if I keep doing it, will result in O of n squared. Plus the rest that I was describing. 1 over n multiplied by the summation from q equal to 1 to n minus 1. And the rest as is. Okay? Now, this is 1 over n multiplied by O of n squared. So this is going to be O of n. Plus the rest of what I'm referring to. Now, what I'm going to do next is I'm going to expand my summation by substituting in the formulation of qs on q plus qs on n minus q. I will substitute from q equal to 1 till n minus 1. So you get this series. And then you apply some basic mathematical reduction to get 2qs plus 2qs plus 2qs, of n minus 1. And this is going to be summation of k equal to 1 till n minus 1 of qs on k, plus some theta of n that I got from the third line up in this chart. Okay? So, what does this look like? The second line from the end. It looks like O of n plus 2 divided by n multiplied by the summation of k equal to 1 n minus 1 qs of k plus theta of n. Okay? This will have to be less than or equal to n log n plus some constant. Now, how can you actually show that? How come this evaluates to this? So this is again a math exercise. I will leave it for you, and there is one problem in the practice assignment that tries to solve something like this, so you can actually work out the math. Okay? I'm not skipping stuff here, I just don't want to tell you everything. If you solve the practice assignment, you will see how you could reach to this. Now, the third example we're going to look at is called the skip list. And this is a very interesting data structure, has become recently very popular. People started using it a lot. And this is a randomized data structure as well. Now, skip list is actually, as the name kind of alludes, it's a variation of linked lists, which you've learned in your early computer science courses. If you remember from your early computer science courses, linked lists were very interesting because we could use them as the base data structure for any program. If you think, for example, of an editor or even PowerPoint, the one I'm using to deliver these lectures, program I'm using to deliver these lectures, PowerPoint consists of slides, and slides consist of texts and bullets and images and so on. So I could code this, the underlying data structure, as a linked lists of linked lists of linked lists. The first linked list is a linked list of slides. Inside it, there's a linked list of text, and so on. Okay? If you think of a word processor, for example, like WinWord. WinWord consists of pages. A Word document consists of pages. A page consists of paragraphs. A paragraph consists of lines, and lines consist of characters. So almost all the editors implementations in the world would go like this, would create the internal data structure as a linked list of pages, of linked lists of paragraphs, of linked lists of lines, of string array or a character array. Okay, so linked lists are very popular, by the way. Now the problem with linked lists is that the performance is O of n. You always go from the beginning to the end of the list because the pointers take you anywhere in memory. It's not like an array where the cells are placed adjacent to each other. The linked list nodes, or link if you remember, is all over the place. We allocate dynamically a memory location and we point to it. It could be anywhere. And consequently, we cannot address a linked list with a square brackets like we do with arrays. We cannot say node 1 or node 2 or node 0 because they're not placed beside each other. So linked lists are very interesting because this is a very natural way to organize the data, to create nesting or hierarchies. But the problem is, it's O of n. So skip lists solve the problem for you. Skip lists is a modified linked list that has many layers, and we will use the layers to jump into the linked list, jump inside the linked list, if you like. And that makes the performance much faster. The first thing we need to learn about skip lists is that they use what's called quad nodes. So if you remember from your data structures course, a linked list would typically have a node with two references, one to the next node and one to the previous node. While what we have here are, apart from the data, there are four references. You still have the next reference and the previous reference, but we also have an upward reference and a downward reference. And what you see at the top figure is an example of a skip lists. As you see, there are multiple levels. They are connected with each other somehow, and some of the values are actually repeating between the levels. And as you also notice, the levels at the top has less nodes compared to the levels at the bottom. The lowest level, which is level 0, will always have all the data items or all the nodes present. So if you'd like to compare this to a doubly linked list, level 0 is a typical doubly linked list. The levels above it are not exactly that. They are created in a certain way. So let's first see the search before we see the creation. So this is how the search proceeds. We always begin with the first node in the top level. So we're always starting at the top level, not at the bottom level. We're always starting at the top level. And we will check the number that we are searching for. And let's say this number is x. And I will check this number with the first node in front of me, which is going to have the value y. If x is equal y, so the number I have actually been looking for has just been found. Okay? And I will stop. And that's obviously a lucky situation because I'm checking the first node in the first level at the top, and I found what I'm looking for. Now, if what I'm looking for is less than what I'm seeing inside the node, if x is less than y, I will drop down one level. If x is greater than y, I will move forward in the same level. So here is an example of a search on the value 78, which exists way at the bottom, far right side of L0. We start always with the top. A skip list has this feature that the leftmost node is always minus infinity, and the rightmost node in every level, this applies, the rightmost node is plus infinity. So I compare 78 with minus infinity. 78 is greater than minus infinity, so I'm still now on L3. So I move forward to the next node in L3, which is the plus infinity. Now, since 78 is less than plus infinity, while I'm still standing on minus infinity, I will drop down one level. I will do the same exercise again. I will compare 78 with minus infinity of L2. 78 is greater than minus infinity, so I will move forward to 31. Now, 31 is also less than 78, so I drop down from 31 to the level below. Now, when I'm standing at 31, before dropping down, I'm going to follow the same approach I just mentioned. When I'm standing on 31, I will check the next node. Now, the next node is plus infinity. 78 is less than plus infinity. I'm referring to the plus infinity at the end of L2. So I always stand at the node and check the one after it at the same level. So 78 is less than plus infinity. Since I'm standing on 31, I will drop down to the level below it to L1. And I will repeat the same process. I'm standing at 31 and I will check the node after it, which is 34. 34 is less than 78, so I will move forward to 34. And then I check the node after it, which is 64. 64 is less than 78, so I will move forward to 64. And then I check the node after it, which is the plus infinity, or 78 is less than plus infinity, so I drop from the node I'm standing in to the 64 at the bottom, which is at L0. Now, when I'm standing at the 64, I will check the node after it, 78, and I'm happy I've just found what I'm looking for. So the merit of skip lists is that they enable you to jump inside, way inside, into the content of the linked list at the bottom level without having to check every single node starting from the beginning to the end. And this is why people got so interested in this data structure, because this enables them to use linked lists as the basic data structure for most of the programs that are out there. It's going to be, instead of a linked lists of linked lists of linked lists, it's going to be skip lists of skip lists of skip lists. Now let's look at the insertion. How does it work? Insertion is done using a randomized algorithm, okay? And it's done in quite a funny way simpler than anything you could imagine, which again adds to the power of skip lists. What we do is we're going to toss a coin and check if it's a head or a tail. And the insertion will be dependent on the output of the tossed coin. Okay? So we will always start by inserting at the bottom layer, because this is actually the storage for all the data. And we are creating the above layers to be able to jump into the linked list at the bottom layer as fast as possible. So we need to have the data inserted at the bottom layer first, and it's a must, because this is actually where we find the data. So based on tossing a coin, if we get a head, we will insert the node we just inserted in the bottom layer in the above layer. If we get a tail, we will stop and we will not insert it. This is how entertaining and simple this could get. So again, I will insert always the entry using the typical insertion mechanism that you've learned in the data structure course in the bottom layer, in layer 0. And the question becomes, am I going to propagate upward to the above layer this value or not? I will toss a coin. If it's a head, I will insert it in the above layer and connect the references appropriately. If it's a tail, I will ignore it. I will not insert it in the above layer. If I insert it in the above layer, I will again toss a coin. And if I get a head again, I will insert it even in the layer above it. If I get a tail, I will stop. It will just be inserted at level 1. So let's see the insertion. Now suppose I would like to insert 10 to this empty skip list. So I will add the 10 to layer 0, because I have no layers now. Okay? We're going to add these layers based on the output of tossing a coin. So I start at the beginning with just layer 0, which is a typical doubly linked list. I will toss a coin after inserting the 10. So you see in the right figure, the 10 has been inserted. And next, what I'm going to do is I'm going to toss a coin. If I get a head, I will create the above layer since it does not exist, layer 1, and I will insert the 10 there as well. Okay? Now, you see now a picture after a while working with this skip list. I've inserted a 10, tossed a coin. It was a tail, so I didn't insert in the above layer. I inserted 23, tossed a coin, I got a head, so I created the layer above and I inserted 23 there. I inserted 36, I got a tail, so I didn't insert it in the above layer. So as you see in the first figure to the left, up in the slide, this is now the picture, this is now the status. I only have 2 layers in my skip list. Now, let's say we would like to insert 15 to this list. So what we're going to do, and we have been doing this previously when we inserted 23 and 36, I would like to find the right place to add the 15. So I'm not going to go and insert it in L0 right away. I will follow the search method that I just showed you, the same approach. I will start always with the top layer, which is layer 1 now, and I will ask, okay, is 15 greater than minus infinity? Yes. So I will move forward to 23? No. We said, if I decide I'm standing now on minus infinity and I have 15, I would like to find its right location, as if I'm searching for 15. So 15 is greater than minus infinity. So I don't move that right away to the 23. Instead, I check while I'm standing on the minus infinity, the next node, which is the 23 node in layer 1. Since 15 is less than 23, I will go and follow from the minus infinity in layer 1 to the minus infinity node in layer 0, and then I will move forward in the linked list to insert the 15 in the right place. And then I toss a coin. If I get a head, I will insert the 15 in the above layer. For the deletion, we're going to do the same strategy. We're going to look up the value by moving from the top left of the highest level, which is L3 in this case, down till we find what we're looking for. So let's say we're trying to delete 34. We stand at minus infinity of L3. 34 is greater than minus infinity, so we check the node to the right, which is the plus infinity in L3. It's greater than 34, so I drop down while I'm standing on minus infinity of L3 to the minus infinity of L2. When I say drop down, well, obviously I can do that because, as you remember, the skip list node is a quad node. It has 4 references, so it has a bottom reference. So I can track that, which appears here in the red color, and I will go down 1 level to L2 minus infinity. And then 34, this is the value I'm trying to delete, is greater than minus infinity, so if it exists to the right of minus infinity. I go and check the next node to minus infinity, and I find actually this is the target I'm trying to delete. Once I find this target, the job becomes easier. I will go and connect the node before and after the target I'm trying to delete, which is what you learned in the data structure course. So I connect the minus infinity of L2 to the plus infinity of L2. And then I go down 1 level, following the reference to the 34 in L1. I will connect the 23 to the plus infinity, and then I go down, follow the reference again. I will connect the 23 to 45 in L0. And that's what you see over there. Now we come to the analysis part. Okay? What we have in skip lists are always log n levels. And this is what makes it so interesting. And the reason why we're having it log n levels, because we are actually cutting the number of items, or the chance of having an item propagate upward in the higher levels. We're cutting that chance significantly as the levels keeps increasing. Okay? So the performance is going to be randomized of O of log n. So I'm telling you up front, the result of the analysis. But let's actually do the analysis to prove that. Okay? If you go back and check the way the skip lists look, they almost look like some kind of a binary search tree or some kind of a binary tree, because the top layer has very few items or nodes, and we keep increasing the number of nodes as we go down 1 level at a time until we hit the leaf level or the last level where all the entries are available. So it almost looks like a tree in some aspects. So the analysis of the search will help us in doing the insertion and deletion, because the randomization that is involved is presented in the insertion, deletion, and search. But with the insertion and deletion, we have additional operations that we are doing, but these are not related to randomization. They are the regular kind of linked list processing of connecting nodes or disconnecting nodes from the linked list of a specific level. Okay? So if we can prove that for the search, the way we are searching, we will always get log n performance, then for sure, since we're using the same algorithm in the insertion and the same algorithm in deletion, also the insertion and deletion will be log n plus some reference manipulation that is insignificant compared to the log n. So let's try to understand what's going in here, okay? Let's insert this sequence 10, 31, 200, 53, 20, 40, 60, 90, 103, 150, 75, 15, 40, 31, 120, okay? Now again, we're going to see the strategy that we discussed. We're going to flip a coin after every insertion and see what is the impact of the insertion of these items. So this is what you see. We start with an empty linked list and we insert a 10, then we flip a coin, we get a tail, so we're not going to propagate it upward or create a new level. Remember, our strategy is after the insertion, we flip a coin. If we get a head, we will insert that element we just inserted, the value, the new value that we just inserted. Before flipping a coin, we will insert it in the above level. If there is no above level, we will create the above level, the next level above, and then we will insert that value. Now, if we get a head, this is what I just mentioned, we're going to create a new level and insert the entry there, but we stop when we get a tail. So I'm going to flip the coin again to see if I'm supposed to insert this new value even in a level above that, the one I just created, the new one. So this is what you see. I insert a head, I flip a coin, I get a tail, I will just keep the head in the lower layer, which is level 0. I insert 31, I flip a coin, I get a head. Oh, so now I need to create a new layer, which is going to be a new level, which is level 1, and I insert the 31 there and connect the 31 in level 1 with the 31 in level 0, because I can follow this pointer later on to go directly to the 31 or anything to the right of 31. Now, because I just had a head by flipping the coin after inserting 31, I will flip the coin one more time. And oh, I'm lucky, I got another head. So I will create even one more layer, which is level 2 or layer 2. And I will insert the 31 and connect now the topmost 31 in level 2 with the 31 in level 1. I continue on, I'll flip a coin, I get a tail, so I will stop creating levels for 31. I will insert the 200, flip a coin, I get a tail, so I'm not going to propagate 200 to the above level. I insert 53, flip a coin, I got a head. So I now put 53 in layer number 1. I flip a coin again, I got a tail, so I'm not going to propagate 53 further up. I insert 20, I flip a coin, I get a tail, so I'm not going to do anything, I just keep it at the bottom layer. I insert 40, I flip a coin, I got a tail, so I'm not going to do anything. I insert 60, flip a coin, I got a head, so I put 60 in level number 1. Next, I flip a coin one more time because I just got a head with 60. So I flip a coin again, I get a tail, so I'm not going to push 60 or propagate 60 to level 2. I insert a 90, flip a coin, I got a tail, so nothing to be done. Insert 103, flip a coin, I got a tail, again nothing to be done. Insert 150, flip a coin, I got a head. Oh, interesting. So I will create 150 entry in L1. Then I have to flip a coin again. Oh, interesting again. I got another head, so I will propagate 150 again in layer number 2. I will insert 75. Oh, I missed. I gotta flip a coin one more time for the 150, but I got a tail, so I'm not gonna create a new level L3 and insert 150 for the 4th time. I insert 75, flip a coin, got a tail, insert 15, flip a coin, get a tail, insert 40. Well, however, 40 is already found. Okay, so insert 31, also 31 is found, so insert 120. Okay, so I get a head after that, so I propagate the 120 upward. Okay, flip a coin, I get another head, so I propagate 120 even further up. Okay, flip a coin again, oh, I got another head, so now I'm going to insert 120 in level 3. Flip a coin again, I will keep flipping the coin with 120 until I get a tail. Now I got a tail, so I'm not going to do anything else to 120. Okay, so this is what the skip list will look like after doing all these insertions. And as you notice, again, this looks like some kind of a binary search tree. Not exactly, there are some missing pointers here and there, but it's not really anymore just a linked list. or a linked list of linked lists. It has its own structure because of this notion of realizing on this random process of flipping coins. Now, let me tell you that skip lists are very, very popular. I've already kind of give you an intro to this. You know that they are now kind of the replacement to doubly linked lists because of their nice performance. Okay, they have all the advantages of doubly linked lists, and the added advantage that you're going to be doing log n processing, randomized log n, I mean. So I already, explained all of this slide. I've kind of introduced skip lists by explaining why linked lists in the first place are so popular, and now you know that skip lists are kind of replacing them because of their performance. So it is an important data structure, by the way, to learn, and you sometimes get questions about it in interviews. You're expected to know it, I would say. Now, here is the big question. We're doing something that seems to be working. That's what we did at the bottom here. And this looks like, if you try to do anything to this linked list, or sorry, skip list that appears at the bottom, this looks like for sure a log n data structure. Because of the jumps and the way we work with it, I will jump directly. If I would like, for example, to access the 200, I will make a few hops and I will find myself at the 200. I don't have to start from the beginning of the linked list at the bottom at level 0 and scan all the entries 10, 15, 20, 31, 40, 53, 60, 75, 90, 103 to 120, 150. Oh, I found the 200. No, this is not how it works. I start from level number, this is level 0, level 1, level 2, level 3, and I jump to the 120, and then I jump to 150, and then I find myself landing at the 200. Okay? So it looks it's going to work. But someone might say, this is going to work because we were lucky. Every time we flipped the coin, we got just a handful of heads and a lot of tails. While there could be another scenario. You keep flipping and you keep getting heads. So more or less you will end up with a picture that looks like what I have put at the beginning, at the top of this slide. Okay, this like horrible kind of linked lists of linked lists where basically they are replicas of each other. All the levels are replicas of each other. So what prevents us from getting O of n squared, and what makes us provide a guarantee that this is actually going to be log n? And this is really what randomized analysis is going to show you. So the general scenario, we're going to analyze the probability of all the elements appearing in all the levels. Isn't that what you're actually afraid of? That we do this random process. We toss a coin, okay? Typical random process. But we end up with an unlucky situation, the disastrous situation where most of the levels are populated with most of the elements. So it becomes O of n squared, of course. This is even worse, by the way, than a linked list. If you just keep it as a doubly linked list, it's going to be O of n. Now with this data structure, if you're so unlucky, it's actually going to be n squared. But the question is that true? And the answer obviously no, it's not true. Okay? So let's see why it's not true. So these are my parameters I'm going to work with. X is a specific element in the skip list. Okay? Some value I have inserted. N are all the elements in the skip list. H is the height of the skip list. Okay? How many levels I have. Okay? Now, the assumptions, the only assumption I will have, no duplicates. As I mentioned before, duplicates are disaster. There is no good way to deal with them. Okay? Apart from setting them aside. Now, here is the main observation. To get the desired randomized log n performance, we need to prove that the height, the h, is equal to log n with high probability. Okay? Now, why am I approaching it this way? I have no control on the heads and tails that will come up. But regardless of what they will come up, if I can prove that h, the height or the number of levels, is always going to be log n, that I'm done. If the height is log n, that I'm going to do log n processing. Okay? And since I got this height of log n using a randomized process, this is going to be a randomized log n, because it will vary from one run to another because of the random values generated, but it's always going to be log n, some kind of log n. So I will set up a random variable x representing the height for element x in the skip list. Okay? I will think of any element. In fact, we can do it for all elements, but let's just pick one element, because one element will be sufficient to explain the idea. So I will set up a random variable that represents the height of x in the skip list. Why this is a random variable? Because the height will vary depending on the outcome of the random process. So it has to be a random variable, okay? So x is the probability of, or big X is the probability of x being in level I. Okay? This is what we use random variables for, to represent and talk about and compute probabilities. So the question becomes, what is the probability that our element x, small x, is in level 0? For sure it is there, so the probability is 1, okay? Because we have to insert it always at the bottom level. The question really becomes interesting when we ask, what's the probability of x is in level 1? Well, it's the probability of x is in level 0, and so it's multiplied by half. Why? Because I'm flipping a coin. To be in level 1, it must be in level 0. So there is always a 1, because it's always in level 0. But to be in level 1, above level 0, that's the result of tossing a coin. And we have two chances, a head or tail. The chance of getting any one of them is half. So the chance of getting a head is half. Okay? So the probability of being in level 1 is the probability of being at level 0 and also being at level 1. The probability of being at level 0 is 1, because we know we have to put it there. It's 100%. It has to be there, okay? But to actually to say and be in level 1, that means we rolled a coin and we got a head. And that's a half. So the probability of x being in level 1 is a half. 1 multiplied by half is a half. Okay? Okay. What's the probability of being in level 2? To reach level 2, it must be in level 0 and must be in level 1 and must be in level 2. Okay? The probability of being in level 1 we already computed is a half. And then we are assuming that we will put it in level 1 and we will put it in level 2. And since, if you remember from your math courses, and when we say and in probability, that means we multiply. So we're going to be standing at level 1 because we got a head, and then we flip the coin again, and then again we get a head, so we put it in level 2. So the chance of at that point in getting a head is half, but the chance of actually being at level 1 is also half. So it's a half by half, it's 1 over 4. Now the probability of being at level 2 is you multiply by another half, so it's 1 over 8. Now what this is telling you is to get a successive series of heads, head, to propagate any specific element upward 3 levels is 1 over 8, which is a weak probability. Okay? In fact, if you think what's the probability of going to level 4, is going to be 1 over 8 multiplied by a half. It's going to be 1 over 16. That's even a weaker probability. Okay? And to think of level 5, that's even worse. It's 1 over 32. Okay? What that means is the chance of a value moving upward and going, say, and creating level number 7 is very, very small, to the point that we can argue it will not happen. And if it happens, it's going to be a rare incident. Okay? Now, the general rule is the probability of x belonging to level I is 1 divided by 2 to the I, where I is the level number. And that's what you see here. 4 is 2 to the 2, 8 is 2 to the 3, and so on. We have been computing the probability of one element jumping many levels upward, but we don't have one element. We have n elements. We have inserted in the linked list n items. Okay? So let me read this. It says, if we want to ask after we have entered n items, what is the probability that a given level has at least one item in it? In other words, the skip list is that high. Okay? The probability that level I has at least one position is at most n multiplied by 1 over 2 to the I. Okay? Why? Because we have n items. Each one of the n items could travel upward by a series of heads to reach some level I. So if we ask for level, say, 6, what's the probability that one item out of the n will reach the level 6? It depends how many times we attempted reaching to level 6. And that means how many items we have, because with every insertion of an item in the linked list, or a value in the linked list, we try to bring it upward, say to level 6. So if we have 100, we have tried 100 times. And if we have 200, we have tried 200 times. Okay? So the probability of some element appearing at level 6 will be dependent on how many items we have. Because all of them will try to go up. We can imagine that all of them are trying to go up to level 6 through a series of coin flips where we get 6 heads or 5 heads in a row. Okay? So the probability of having one element at level I is n, all of them, because all of them will compete for that, multiplied by the chance of any one of them going to that level, which already we discussed in the previous slide to be 1 over 2 to the I, the height of that level. Okay? Now, why am I doing a multiplication here? Why am I doing addition? Okay? Because each one of them has an equal probability to go to that, because I'm saying at least one. I'm saying at least one. Okay? So we could have 2 or 3 or 4 or 5 or 6. So each one of them has a probability of going up there. So it is this and this and this and that and that and that and so on for all of them. That's why it's n multiplied by the chance. Okay? So I have n chances where each chance probability of success is 1 over 2 to the I. Okay? Now, the probability of an item reaching some level I, or at least one item reaching some level I, is going to be, as we mentioned in the previous slide, n multiplied by 1 divided by 2 to the I. Okay? Now, we are interested in showing that the skip list do not get more than some log n height. So I will assume my height is log n. Or in other words, my I, the level I'm interested in, is log n. So if I have 1,000 elements, I'm interested in finding out what's the chance of actually having an element at log 100. Okay? So I'm interested in calculating the probability of at least one item going to level log 100, whatever that amounts to. Okay? Now, I will just substitute the I with log n in the equation we were just looking at. So it's going to be n divided by 2 to the constant multiplied by 2 to the power of c multiplied by log n. Okay? And then I will play some tricks with the power and logs. So really I'm talking about n divided by n to the constant. So really I'm talking about 1 divided by n to the constant minus 1. That's the probability of at least one element going up all the way till log n or log 100 if I have 100 values. So let's plug in some numbers here. Okay? Let's say that the constant is 3. Okay? And let's say my n is 1000. So what that means, let's plug in the numbers and try to understand this. If I have a linked list of 1000 nodes, the probability of being or of having at least one element that is higher than 3 log n is going to be 1 over a million. Okay? How is this coming along? I have computed that the probability of at least one element going upward all the way till log n is 1 over n squared. Where is 1 over n squared coming from? It's coming from n divided by n cubed. Where is the n cubed coming from? The n cubed is basically, I had 2 to the power of log n cubed. So I apply, the logarithmic rule, and that reduces to n to the 3. Okay? Now, where is n to the 3 is coming from? Why am I having 2 to the power of log n to the power of 3? If you look at the previous step, it was 2 to the power of 3 log n. I took the power and I raised the power to the n. This is again logarithmic manipulation. Where is the 3 coming from? I'm just trying out a value that I am bounding the solution by. Okay? Now, if you go up one line to the first line in the slide, it says the probability of some element, at least one element, going up to c log n. Why do I have a constant? Because our skip list is not perfect log n. Okay? We have seen that in many examples. It's not perfect log n. Okay? It's a log n multiplied by some constant. Okay? But it's not a big constant because we're not really seeing a large tree. In fact, we are seeing quite a squashed tree. But it's not an ideal log n where you have the same number of children on every side at every level. Okay? It's even more squashed than that. So it's going to be some constant multiplied by log n, and the constant has to be small. So I'm assuming here it's going to be 3. I could assume it's going to be 4 or 5. And in fact, 3 is a conservative value. I'm not putting it to prove my case. I'm putting it to show how strong my case is, because C is a very conservative value, being 3. Okay? But if we plug in the numbers with 3, just with 3, we're talking about the probability of some element going upward all the way to level 3 log n. So if we have 1,000 nodes in the linked list, we're talking about the probability of some element, at least one element, going upward all the way to a height of 3 log 1,000. That's going to be, substituting in the values here, it's going to be 1 over n squared. That's going to be 1 over 1,000 squared. That's going to be 1 over a million. Okay? Now, if you'd like to see a real case, put n with 4. Sorry, put c with 4. Now, c with 4, as it's highlighted in the bottom point, that's going to be 1 over 1,000 to the 3, to the power of 3. Okay? Just plug in the numbers. And this is why skip lists are so interesting. Because, just to sum up, the chance of you getting a sequence of heads is very, very small. A sequence of successive heads. To get one head, that's half. To get a second head after it, it's 1 over 4. To get a third head after it, it's 1 over 8. To get even a fourth head after it is 1 over 16. Okay? And the chance of that happening to all the elements is even smaller. That all the linked list entries, every time you flip a coin, you get a head. So the first one you do, you get 4 heads and success. And then you flip the next one 4 times and you get 4 heads and success, and so on. It's just ridiculously small, and this is what all this formula is showing. I will conclude today's lecture by references to randomized analysis from the Corman textbook, and 2 references to the Goodrich and Tamassia textbook for quicksort and skip list analysis. So please read them. They have detailed description of what I have discussed in case you have any wonders about randomized analysis.